This is the first video that I'm posting in 2026, and the first thing that I want to say is that 2026 is a really boring number. You try to factor it and then there's like nothing going on. There's a 2 and a big prime number. 2027 is going to be even more boring because it is just a prime number. But if you compare that to 2025, that one was really interesting. It had a bunch of small prime factors, 3s and 5s. And of course, you can say it's a matter of opinion which ones of these are interesting or boring. You could say that a prime number is interesting, but the difference that I'm trying to point out, it's clear. One of them, you touch it and it crumbles like sand into a tiny little pieces, and the other number is just one big block. But what's really interesting, I think, is how numbers that are right next to each other have these completely different behaviors. This, of course, happens much earlier on. We don't have to be talking about large numbers like 2026. Look, two different primes, then an unrelated prime, and then three of the same. Probably my favorite example is 168 and 169. Neither one is prime, but they break apart in very different ways. So the point of this video is going to be to talk about why this matters, why I think this is an interesting thing, and what will be the implications of thinking about these things to everybody's math understanding in general. Yes, these are cute little things to look at, but that's not the only reason why I'm looking at them. I used to think that none of this would matter because even when I say that I am interested in numbers that are right next to each other but look completely different, what does it mean to be right next to another number? This is a thing that only makes sense in the integers. And most of the math we do later on happens in the real numbers. So yes, if you're looking at the number line and just paying attention to the integers, 168 and 169 are right next to each other. But in the real line, there's all sorts of numbers in between them, right? There is no being right next to another number because any two real numbers that you take, there are others in between. For example, you could take their average and that's another real number. So there is no being right next to anybody. The other thing that doesn't work in real numbers is when you want to talk about when a number is a multiple of another number. So for example, 168 is a multiple of 7 because there is a value of k that multiplied by 7 can make 168. And that number, of course, is 24. But in the real numbers, if you think about things that way, then everybody is a multiple of everybody. 7 is a multiple of 3 because there is a value of k in the real numbers. That makes this equality true, which is the number 7/3. You didn't even need the real numbers for this one. Rationals would do. But you could also say weird things like the square root of 5 is a multiple of pi, right? Because you just have to multiply it by the number root 5 divided by pi. So the concept of being right next to doesn't exist in the real numbers. The concept of being a multiple of also doesn't make any sense. And most of the interesting math we do in life is with the real numbers. We use real numbers when we talk about functions, which is arguably the most important thing that you can do in math because that's how you model processes from real life. You use real numbers when you take a point in that function and draw a tangent line and then you start doing calculus. That's all working with real numbers and it's very important. So why should this matter? Why do I still want to talk to you about factoring numbers? Who is a multiple of who? It feels like something that we did in math class when we were children, and it was a game, it was for fun. But it goes back to what I was talking about, why I'm calling some numbers interesting and others boring, and why I'm so interested in the fact that numbers that are right next to each other have nothing to do with each other. And what do I even mean by have nothing to do with each other? Just because their prime factorizations are different. But the thing is that I want you to think about the way that the number breaks apart in a multiplication. That's who the number is. When you do 2025 plus 1 and then you get 2026, well, of course, 2025 plus 1 is equal to 2026, but that is not who the number 2026 is. He is 2 times 1013. So let's look at the number 12, for example. 12 is 2 times 2 times 3. 12 is many other things, such as 5 plus 7, but I want to try to convince you that this doesn't matter. When you're adding, you are moving along the number line. You start from 0 and then you do 5, so you move 5 steps to the right, and then plus 7, it's another 7 steps to the right. There you go, you are at 12. You could have done that in many different ways if you wanted. If you allow moving to the left as well, then there's an infinite number of ways that you can do it, because if you pass the 12, then you can always go back. This is 8 plus 2 plus 5 minus 3. That's also 12. So that's not interesting. That is not 12's identity. That's not who he is. It's not his essence. These are just multiple ways to get from here to there. Who is 12? 12 is 2 times 2 times 3. No matter how you get there, which path you take by adding and subtracting, every time you get to 12, he's going to be 2, 2, 3. There's no other way to think about him. And he really is that, even though he is squished between two other numbers, 11 and 13, who are their own thing. They are prime numbers. And this uniqueness matters, the fact that there is only one way to do it. Addition doesn't matter. Addition, you can get to the same number in a lot of different ways, and it doesn't mean anything. Multiplication has this uniqueness about it. And yes, I am restricting myself to the integers for this conversation, okay? There is only one way to break apart a number. And you could say, oh, but 12 is also 6 times 2. Well, yes, but the 6 itself can also be broken apart into 2 and 3. So if you think 6 times 2, then it's 2 times 3 times 2, which is the same thing as 2 times 2 times 3, because the order doesn't matter when you're multiplying numbers. So another reason why I was saying that the numbers that can be broken apart more, I think they're more interesting, is because you can draw them like area. For example, 6 is 2 times 3, so you can think of that as a little rectangle. You cannot do that with 5. 5 is just 5. So it's just one long thing like that. But when you get to 12, which breaks apart into 3 factors, that's even more interesting, because you can draw it like a three-dimensional little block thingy. 2025, then you would need 6 dimensions to draw this thing. I'm not going to try, but isn't that interesting? 2026 is boring. It's a rectangle, but it's like a really long rectangle. And 2027, there's nothing you can do about it. It's just a stick. It's like the only thing that we know about numbers is putting them together. It's 1 plus 1 plus 1 plus 1, 2027 times. We don't know that we can multiply things to get there faster. Like 4 times 3 is 12. You don't have to go one by one. So besides uniqueness, the other reason why multiplication is nice is because it doesn't change what the number used to be. It just adds complexity to it. So for example, you start from a 3. You had a 3 here. This is 3. And then you multiply it by 2. The 3 is still there, but now it is multiplied by 2, and it is a rectangle, one of whose sides is 3. So the 3 is still there. Then you have your 6 here, right? And then you multiply it by 2, but the 6 is still there. Look, the 2 times 3 rectangle is still that side of the block. It's just that now you are adding another dimension of 2 in a perpendicular way. So you're building the number dimension by dimension in this way. Adding is like throwing a bomb at the number and exploding it, and you're going to build it entirely from scratch again. Like 6 plus 1 is 7. Where did the 3 go? Where did the 2 go? 7 is just going to be like a little straight thing like this. It doesn't have any area. It's not interesting. If you want yet another way to visualize the way that the multiplication is building the numbers, is that instead of putting the numbers in a straight line like this, where you go to the right, always plus 1, plus 1, plus 1, in always this same way, well, you're not going to be able to start from 0 in multiplication, right? But you're going to start from 1. And then you can think that as you multiply by different numbers, you get different numbers. So if you multiply 1 by 2, you get 2. If you multiply 1 by 3, you get 3. But the 4 is not going to come from there. The 4 is going to come from here, from multiplying the 2 by another 2. And then this is a fun game to play as children. I don't know how old you are. I don't know if you're going to find this fun, but I certainly did and still do. Where is the 5? The 5 is someplace else, right? It's here. But where is the 6 now? Well, the 6 is built from the 2 and the 3, so it kind of has to come from both. I don't know what color to write the 6 in, but the edges I am putting in the colors that are representing the prime numbers. Okay, so where is 7? 7 is a new prime number right here. 8 is red, definitely, completely red. Where is 9? Oh, 9 is yellow. What about 10? Well, 10 needs to come both from the 2 and the 5, so I'm going to put him here. 5 times 2 is 10, and a green line from 2 to 10. There you go. 11 is a completely new number down here. And where is 12? Well, figure it out. Right now, artistically, it begins to get a little bit complicated, and that's why it's fun. This is a game that you should play if you want to become more familiar with how these numbers are built. I don't know, I've gone a little farther here. I would need a new color for 17 now. So anyway, those are the reasons why I think compositive numbers are more interesting. Now, why does this matter? The thing is that you have to understand that multiplication is who the number is. It's how you build numbers. Addition is just an annoying thing that is there, breaking all of our patterns. We had 168 and then suddenly plus 1, now it's 169, completely different. So multiplication is the good operation. This is what's important to keep in mind. So when you're doing something like this calculation on the right here, you had a 2 times 5, which is good. It's just 10, right? It's who the number 10 is. And then you're multiplying by 3, so you're just putting another little block onto it. It's still who the number is. This is 30. But in this calculation on the left, that's not what's going on. This is 21. This 2 plus 5 is 7. So this is actually 3 times 7, but it doesn't look like that right now because we can't see the 7. And we can't see him because of this annoying plus in there. When I was in the other one, I could clearly see the 10. Here's the 10. So of course you can do the addition first and now you can see the 7, but that's not what I'm going to do because I'm not interested in working with numbers. I'm interested in working with letters. Let's get this 5 out of here and put an X in his place. When it's multiplication, absolutely nothing changes. I don't really know explicitly what the number is, but I can still see him. It's here. It's whatever number you get when you take the X and just add one little more block of 2 to it. But here, this is invisible. 2 plus X can be absolutely anything. If X was 5, then I'm getting 7, which is a prime number like I was doing before. But if X is 10, now 2 plus 10 is 12, which is 2, 2, 3. It's a completely different number. Addition is annoying when it appears in calculations. And I do feel that it is important for students to feel annoyed by that because that is the reason that justifies why you need to use distributive property in such situations, but not in this one, because most students have been trained to memorize these rules. So when there's a number multiplying a parentheses, they know that sometimes you need to use distributive property. And then the students that are considered good are the ones that never forget that this is what you're supposed to do when there's a plus inside of a parenthesis, but not when there's a times inside of there. The students who are considered bad are the ones who sometimes forget this random arbitrary rule and end up doing a distributive on a multiplication, which is wrong. But your math ability shouldn't be about whether you are more able to remember or forget arbitrary stuff. This is not what math is about. So I've spent the past, 15 minutes talking to you about weird stuff, such as who the number actually is and what is the essence of the number versus just doing operations to get there. And I know that sounds weird. Okay, I am aware that I sound a little bit crazy when I talk like that. But it is the way that I think about numbers. It always has been. And I am a person who is considered good at math. So I'm trying to give you this chance. And another thing that sometimes leads to mistakes at this point is that the calculation on the right looks a lot more finished than the one on the left. And this makes a lot of students nervous. So maybe you're perfectly fine with your answer to the question being 6x, but 6 plus 3x looks like there should be something else that you could do. It looks like it should be simplified more or else it's not ready. If you're getting this kind of feeling, I guess that's a good sign because at least you are sensing that the plus is annoying, right? The plus is annoying you. Because yes, the answer on the right does look better. It is a full number. It is 6 times x. And the number on the left, we don't know what number this is in the same sense that we've been talking about the other examples. Okay, there was a thing that was 3x. One of the factors was 3 and the other ones were the same as the ones from x. But then you added 6, so now it's a completely different number. It's good if you're getting this kind of feeling that one looks finished and the other one doesn't. What is not good if that leads you to making a mistake, because I see some people that go ahead and say 9x here. Of course, this is absolutely wrong, because that is not what addition does to a number. It doesn't keep the 3x and then multiply by another thing. A lot of times I will give my students something simple as a quadratic equation to solve, or it will appear in the end of another more complicated question that was about something else. And they have memorized the quadratic formula, right? They like the quadratic formula because they don't forget it. So they take this thing, they distribute whatever needs to be distributed, and then they throw that into the quadratic formula. It's going to be a mess because I've chosen two answers that are fractions that have nothing to do with each other. But the thing is that when you did that, you have destroyed the information that you were looking at. You were looking at a product. A product. This is the essence. This is who the left side of your equation is. It is this multiplied by that. Now all that you can see is two additions, and this number can be anything. 168, which is so pretty. You do plus 1 and then suddenly it's 13 times 13. Now you look at 6x squared plus 11x and then you do minus 35. That can be anything. That gives you no information about what the factors are that you were looking for. I'm not going to do that, of course, but I will tell you that if 2x plus 7 is equal to 0, then x needs to be negative 7 halves. And if 3x minus 5 equals 0, then x needs to be equals to 5 over 3, which are the solutions to the quadratic equation. This is the easy kind of equation. Sometimes you make a problem a lot more complicated than it needs to be because you refuse to see the structure behind the original problem, because you're not thinking of the structure of who the numbers actually are versus just symbols on a page that happen to become a number when you calculate them. The really annoying quadratic equations are the ones that are not equal to 0, right? Because you look at the left-hand side of this equation and you can clearly see roots for that. It's the two fractions that I just told you. But then when you subtract 1 from that, the whole structure is broken. Now it's a completely different number, and it's unpredictable what number this is. Because when you add 1, when you subtract 1, the factorizations of the numbers, they change wildly. There is no pattern to it. Addition is annoying because it doesn't have a pattern. Multiplication works very pretty with all of the patterns. So when you do run into something like that, there is no option. There is nothing you can do but destroy the structure, which I just did by doing this distributive. And then you're going to put the 1 together with the 35 here. And we are aware that this is a completely different structure. Knowing or being able to easily get to the solutions to this side doesn't help you at all to get the solutions to this one, because plus 1 is now a completely different thing. So distributive is easy. Destroying things is easy. What is difficult is building things. Is what you have to do now is to find a new structure. What is this one? And factoring is really difficult, except when it comes from a question in which the numbers were very carefully chosen to be easy, right? Which I did not do just now. So if I was really trying to solve this equation, now is the time when I would actually use the quadratic formula. Now it is not too strong of a tool for the problem at hand. And the other type of situation in which I sometimes see people making a simple problem a lot more complicated by using distributive is when the polynomial equation is not of degree 2. Okay, this one is degree 3. And unfortunately, there are a lot of people who start by doing distributive on this thing. I am not going to tell you how I did this expansion right now. You can either just do it by hand as x plus 2 times x plus 2 and then times x plus 2 again, or you can go check out my video about the binomial theorem. But for right now, just trust me that this is correct, and look at this. This didn't help at all in solving the equation. We don't know what to do here. We could try to subtract an 8 from both sides, or subtract the 27 from both sides, whatever, but this doesn't help because this is now a polynomial of degree 3, and we don't know an equivalent to the quadratic formula for degree 3. So this is interesting because in the previous case, it at least works. It becomes more difficult, but it works. You distribute the factors and then you use the quadratic formula and you get to the answer. But for this degree 3 example, it just doesn't work because you don't have a formula. And this is not the most relevant thing for this video today, but the correct way to solve this equation is to take the cubic root on both sides and then subtract 2 from both sides. I also have another video about this, solving this type of equation. But the point is that this is why distributive is easy and factoring is hard, is because breaking stuff is easy, building stuff is hard. So I hope to convince you that the stuff is the multiplication. This is what is the structure. Addition is an annoying operation which we don't like. When you convince yourself of that, you're going to stop making silly mistakes such as canceling this x with this x. This is wrong. If x was 168, then this fraction would be 169 divided by 168. These are completely different numbers. There is nothing to cancel. I know it looks originally like they are kind of similar because they both have an x. There's an x here and there's an x here, so they must have something to do with each other. It makes you feel like you want to cancel things out. There must be a simplified version of that. There must be a way to simplify the expression. But you're feeling this way because you haven't internalized the fact that addition doesn't build the number. In fact, addition is most of the time breaking the number, right? That's what we've been talking about. And this should not be a memorized arbitrary rule in which you memorize something like, well, I can only cancel the top and the bottom of a fraction if there is no plus on the numerator, or something like that. Please don't memorize that. None of this is arbitrary. It's just consequences of feeling the numbers for who they are. There's a thing that I do sometimes that my students find super annoying. This calculation is from another video, okay? I was trying to solve this equation, and then I expanded both sides, and suddenly there is an 18 squared here. Whenever this happens, I annoy my students because I do not calculate 18 times 18. Who wants to do that? So I just keep the 18 squared in there and hope to handle him later. And this is the part that I didn't do in the other video because it wasn't the point. It wasn't relevant there. But how did I solve this equation? My sequence of steps is sometimes unusual. It's not what my students expected to see, even if they agree with each step, and that's why they're annoyed with me. So on the first line here, I divided both sides of the equation by 4. But why 4? There was an 8 on the right-hand side. Why not 8? So the thing is that I'm trying to keep in mind who all of these numbers are and trying to make them as small as possible so that I don't have to actually do any calculations that I can't handle in my head. So what I did here was I realized that 18 squared, well, 18 is 2 times 9, right? So it's 2 times 9 times 2 times 9. The reason why I'm able to act this way with the calculations is because I'm constantly thinking of who the numbers are. The 36 is 9 times 4, which is convenient because of the 4. And if I'm spelling things out, I guess I should also rewrite the 8s as 4 times 2. This is always what I'm doing in my head when I start to solve equations really fast by doing unexpected steps. I don't often spell it out like this, but now you can see that everybody has a 4, right? This guy has this 4, here's a 4, 4, 4, and that's why I decided to divide both sides of the equation by 4. Now this side has a 2 and this side doesn't. It's all 9s. 9s are odd numbers. It's 3 times 3. But there was a minus there, right? So it's an odd number minus another odd number. That is going to make an even number. So I decided to break that structure a little bit in order to build a new structure that is going to have an even number. Again, I did not write this down, but I factored out a 9 from both of these parts here. So it's 9 times 9 minus 1, and that is what is making this 8. Now I divided both sides of the equation by 2 because there's an 8, a 2, a 2, so the 8 became a 4 in the following line. 9 times 4 is 36, and that was the end of my exercise because this is z squared and I wanted to find z. So square root on both sides, z was 6.